I can go live. Only thing unclear. I think that it is very good. It looks so. It looks that this chroma key is not perfect, but it's okay. I think it is good enough. Good enough. Okay, so you have a phone with you.
Yeah.
So can you take a look how did it look? Yeah, I'm alive. That's how it look. It's
Yeah.
it's okay.
Yeah.
I think that it is okay. So the chroma key is not perfect, but it's not very bad either. I think that it is.
Background is like.
And can you put the can you hear me? Yeah. Is it okay? Still not okay. You don't hear me.
Oh,
Oh,
okay.
you do hear
Yeah.
me.
Now
So
it's okay.
it comes with a major delay. So that's a. I think that it is okay. Okay. Hey, thank you.
I'll be here.
You're gonna be here?
Yeah.
Okay, so can you please use your computers to see if there's any comments from online participants?
Yeah. Yeah. And I'll let you know.
All right, very good, very good. Okay, guys, I think we're all done with the settings, so we're good to go. So it's looking okay.
Yeah.
Do I look strong? Do I look young?
As always.
What I was clever? Not that. Okay, respect. Okay, so I need. Oh yeah, I know, I know. Let me make another start. Better. Wall is visible. I don't want to take this. Oh, you guys don't see me, so I still need to make a one more thing here. Projector is not yet on. It's just a second. Look at this. Somebody's thinking that this is a whiteboard. It should be coming momentarily. It is on. Okay, but why is that you don't see anything at all? Is it because of this thing again? No. So you. Okay, is this okay? Is this bothering you or is it okay? This one is okay. How is my head? Do I look pretty? Still visible. Yeah, you're gonna put them a little bit down because it needs to be perfect. Because amount of people that this is gonna be displayed is like that much. That much. Okay. Let me lift this. So it should be perfect momentarily. So now it's perfect. Okay, another start. Respect. Good to see you guys again. I was missing you. So it was a hard week to be without you, but I survived. Finally back in the business. So we have another 6 weeks time to enjoy about simulation. So what follows is that this is going to be the last lecture about the mechanical modeling. But I still want to make an opportunity, use this last opportunity to explain you something I feel is important. And what I wanted to explain to you is how is that you can solve the equation of motion, or how is that you can express the equation of motion using a minimum number of coordinates. This is something that is taking us back to the concept of virtual work. And when I was introducing this concept to you, I mentioned in the very beginning that this is very often misused. And I said that it's very often misused because you can only set the virtual work done by inertia and external applied forces to be equal to 0 if your virtual displacement is kinematically admissible. At the time, there were no way that you understood what I said, so it was complete nonsense. But I want to revisit this statement because this is something that's going to help you whatever you're going to look at the mechanical problems in future. So I'm going to use this last opportunity to tell you about how you can create the equation of motion in an alternative way, the way that is based on minimum number of differential equations. And this is going to be the method that is called embedded technique. So embedded means that we are embedding, meaning substituting the constraint equations inside of the equation of motion. When doing so, we're going to get the minimum number of differential equations. And this is a technique that you can use, not just in solving the dynamic equilibrium, but you can use also to find a static equilibrium. So pretty useful technique. And I just wanted to revisit to make sure that you have a full understanding about the mechanics. And then what follows after that is we're going to leave the box that is color coded here by red color. So this one, we're going to put this in a side. We're going to start looking something completely different. And something completely different will be this box, actuators. And the rest of the course will be more or less devoted to actuator modeling. You know, there's many different kind of actuators. And the most commonly used when we're discussing about heavy machinery are hydraulic actuators. We're going to focus on hydraulic ones. But with the minor additions, what I'm explaining about the hydraulics, you could use the techniques also in the pneumatic drives. But the pneumatic actuators are not often used, particularly not often used in a heavy machinery. And that's the reason, of course, is very clear. And the reason is that the air is more than 1,000 times more flexible than the fluid, oil. And that's a major difference. And because of this flexibility, pneumatic actuators are typically too soft. More accurate term would be more flexible, too flexible to be used within the heavy machinery. They are used in certain applications like on-off, like door open, door closed. But something like which is like mechatronics that you can control it in all possible positions of the door. So those are not so often used. Of course, something that is very much in a fashion today is electric drives. If we have a time, we can touch that subject matter a little bit, but mainly we're going to focus on hydraulics. And how is it we can model the hydraulics? This is extremely important, extremely important. And why is that? Because, if we're going to really simplify the case, so far we've been studying this box. And this box, when you take yourself back to the Newton's second law, you remember the Newton's second law was such that there is always mass multiplied by acceleration. So this is r dot dot. This is inertial forces is equal than external applied forces. Mechanical structure typically is responsible of this particular part. So this is related to mechanics and where the forces are coming from. They are coming from actuators. And you understand that if this equation, this F force, is something that you're guessing or you don't know how much is a force, the value of this equation is Not much. It's something that actually the whole concept of simulation makes no sense because if you're solving the acceleration by guessing how much is external applied force is, the value and how accurate is the simulation is next to nothing. So this is making no sense. So what we actually need to do here is that we need to look at the machine as it is, assembled machine. And we need to start looking at how much is the force that is coming from different type of the actuators. What is the actual numerical value of the force? How the force is changing as a function of time. So that's why the actuator modeling is so critical, so important. And of course, you know that it's not just these two components, but control scheme is something that often makes a major difference. User can make a major difference. This control scheme is something that we don't touch much of this course. We do gonna touch this one, which is a user. And the user can be accounted when you're synchronizing the solution to real time, which is called real-time simulation. So it's pretty much what we have learned so far, but with the difference that the solution is synchronized to actual time. This is something that allows you to take a user into account. And there's something we are not going to touch this course. It's going to be the working process or the environment. So this is something that will be left for the course that is the best course of this university. So if you make a list of really the best courses that this university can offer, the list is as follows. First comes simulation laboratory course, the one that I'm responsible of. Then comes nothing. Then there is a big gap, and slowly other courses. So this is in own league. So it's absolutely in own league. This course is getting started in January. Think about it to participate. All right. Anyway, so this is something that the contact modeling and others is going to be touched in the course that is getting started in January. All right, but still we are middle of the task. We need to start looking this guy. And that's what the rest of the course is about. But something that is extremely important for you to understand is this. Grading. Remember, some of you may think that I'm off the hook. I can finally breathe. I can relax because I scored this and this well. I learned that, some of the guys scoring 5 out of 5 from midterm exam, which is, it's fantastic. It's really is great. It's hard me to even believe that somebody can score 5 out of 5 because the exam is difficult. It is really, really difficult. And now you might think that, okay, so I figured out everything a while ago. I can take it easy. I don't need to work anymore. And that's where you are wrong. Because look, the grading is composed of 3 major components. Written exam, which you have not completed. You have not, because you made a first midterm exam. There's another midterm exam to come. So you need to do them both. And that's when you can say, finally, 35% of my course is done. 35%. Not much. You need to look at this weekly homework. Weekly homework is something that is continuing the second period, but only for, what is it? Is it 2 or 3 more weeks? And then we're done. Then we are not doing this weekly homework anymore. And then there's a simulation work that will be given to you. Was it this? No, it's going to be next week, if I remember correctly. This is something that it's going to be individually made. So there will be initial values that is based on your student number, and we're expecting you to do that by yourself. You have multiple choices. What comes in a software that you can use. You can use a MEVA software, which is these real-time simulators that are located in the corridors are all based on MEVA software. You can use this Simscape, and you can use a Chrono. Chrono is an open source software. There's going to be introduction about the Chrono a little later in this class. Okay, this is it. So, lesson learned. You're not off the hook. So don't start developing something that is very, very dangerous. Something that is extremely dangerous is up-nose attitude. Don't think about it. Oh my God, I'm so good that I figure out, I don't need to work anymore. You do need to work. You still need to follow the lectures because level of difficulty, this famous LD, continues to be challenging. So there's a few things that are not simple to understand what comes in a hydraulic model. It's getting started next week. This week is going to be pleasant. Not pleasant, but let's say hydraulic modeling perspective is going to be simple, but it's getting to be increasingly difficult again. We are not going to go top of the mountain anymore, but it's going to be something that you need to follow to be able to survive. Okay. All right. Any comments, questions about the midterm exam, by the way? Was it simple? Was it something that you expected to see? Was it too difficult? Nice. Nice to be back. Nice to have this, again, this nice kind of like friendly environment. This was exactly what I was missing. So exam was lovely. So what did you feel that it was difficult or it was okay? Okay.
I like the way that you had two chances.
Yeah. Yeah, that I think is a nice thing. The problem I need to admit is this, that it's still black and white. It's correct or not correct. That's not good. That's not good. It's supposed to be like weekly assignments that if not able to answer correctly first time, you will get the hint and your points will go down, but you're still not going all the way down to the zero. Because I feel that's a little bit excessive. That if not able to answer correctly, then you get nothing. The problem is, the one thing that makes your life a bit easier is that you have a lot of questions. So even if you missed one, you still have many to go. So, all right. Anyways, embedded techniques. So let's discuss about one more thing about mechanical modeling. And you guys, I can tell from your face, like, what? You promised no more mechanical modeling. I did, but sometimes you cannot trust me because, I have my desires to continue my stuff because the multi-body, you know how much I love that. And I'm thinking this, that I'm going to change my middle name to be multi-body. So it's Aki Multi-Body Mikkola. That would be more describing me than anything else. So one more effort about multi-body, and then we're going to move on to hydraulics, which is not my middle name, but I still like the modeling of hydraulic components. Let's take ourselves back to mathematics. Remember, when was it? 3 weeks, 4 weeks back, we look at the minimization problem with the constraint. So we look at the same function we're looking today to. So there is a function q, which is a 1 divided by 2, y1 power 1 power 2, y2 power 2. This is your function. You need to minimize this function in such a way that you need to take this constraint into account. So y1 minus y2 equal to 0. We saw this earlier by using the concept of Lagrange multipliers. Now this was this concept that we looking there. There's like gradients of the two components. Sorry about that. Two components. And we said we look at where they are in the same location, we make them to be equal in length. And that was the way we introduced the Lagrange multipliers. Now we're going to do something different. Remember, 4 weeks back, we solved the problem by using substitution technique. So we substitute the constraints to original function. And it went like this. So first, you're solving your constraints. From your constraint, you're solving y2. Once you're done with that, you substitute y2 to your original equation. And then you differentiate the equation with respect to only variable you have, which of course, in this case, is y1. You set this to be equal to 0, and you're able to solve your first variable, which is going to be y1. So it's simple like this. You redo the thing, but this time you're solving the y1, and you substitute it, you're solving this one, you substituted that here, which is this one here, and now this, and then you can solve the y2 by differentiating everything with respect to variable, only one you have in your system. And then you're able to solve another equation. How you do the same, but in mechanics, it goes like this. We take ourselves back to the equation of motion, and we take ourselves back to where we said this virtual work. This was the equation we end up to be. Remember, So we say that virtual displacement of all the coordinates multiplied by generalized inertia forces minus generalized externally applied forces is something. Unclear what it is. And I said that the concept of virtual work is often misused because in general case, as this virtual displacement goes in all possible directions, is not equal to zero because the constraints are not obeyed. You're going against the constraint. That's clear because if you have like, let's say pendulum like this, you're moving pendulum to x direction, it's going to be like this. So you're breaking your system, and that's why the constraints are actually working. The only way to set this to be equal to zero is to set this virtual displacement, which is this guy, such the way that it is kinematically possible, kinematically admissible. Okay. Now, pendulum is clear. Kinematically admissible is this. That makes sense. What if you have more complicated mechanisms? 4-bar mechanism is not so simple to define what is a motion that all the constraints are fulfilled. Crankshaft mechanism, seemingly simple mechanism, but it's not so simple to say, okay, what kind of displacement exactly is the displacement that is kinematically possible, displacement that fulfill the constraints. We all understand how they look in real life, but how is it you can express that mathematically? That's a challenge. And there is a way to make it happen. And the way you can make it happen is that you can categorize your coordinates to 2 different categories. And these categories are dependent coordinates and independent coordinates. How you do that? Actually, you can do this almost any way you want. There's going to be a certain limitations, which I'm going to explain to you momentarily. But basically, you can do this categorization. Theoretically, you can do it as you want. All the thing that matters here is that you need to make sure that the number of independent coordinates must be equal than the number of degrees of freedom. So that's the only thing that matters. Rest going to be dependent. Why is it like that? It's going to be like that because, if I have 1 degrees of freedom system and I'm moving this 1 degrees of freedom, so I can select any coordinates what I want, but the rest of the coordinates are no longer able to move as they want, but they have to move according to constraints. So this is where that is coming from. Yes, sir. Yes, because I was looking at your face and I see that some of you are mentally screaming like, oh my God, I will not survive anymore, so this is too much. First promise that it's going to be sun shining and everything, long daylights and beach weather like this. You can look at outside, there's nothing but like that. Okay, all right, so I just say that, what we need to do is that we need to select the number of independent coordinates such that they match the number of degrees of freedom. Example is this. If I have here a pendulum, revolute joint here, number of degrees of freedom is going to be 1. Correct. So it's 1 degrees of freedom. All right. Now you have here Rx, Ry, and angle theta. So you have 3 generalized coordinates. So which out of these three generalized coordinates is the one that is freely capable to move? Whatever you want. You can select, if you want, you can select this one to be the one that is freely movable. But the rest are no longer free to move as they want. But they have to move according to revolute joint here. Or if you say that, actually, I'm not happy about that selection, I want angle theta to be the independent one, fine. But the rest need to be solved by using constraints. And when you do so, then you can say that the displacement is kinematically possible, kinematically admissible. Then the motion is for sure something that the system can do because all the dependent coordinates are solved using constraints. So that's how That's what we're going to do. And this is the method that is called this embedded technique, where the constraints are embedded inside of the equation of motion. I said that dependent coordinates need to be solved using constraints. Where are the constraints? They are not here. So what was the representation of constraints? Jacobian matrix. That is the one that is telling the constraints. So, okay, what about we do this? Oh, there's in-class quiz. Let me get back to this in-class quiz momentarily, because I was about to explain about where the constraints. The constraints are Jacobian matrix. So what we need to do here is that we need to break the Jacobian matrix in a way that there is going to be a part that is related to dependent part and independent part. This division, again, theoretically you can do as you want, but theoretically only. In real life, this division will be based on Gaussian elimination with the full pivoting. This is how you can do this selection automatically, or is made for you. Let's put it this way. Okay, but if you do this coordinate partitioning to Jacobian matrix, or you apply this to Jacobian matrix, and if you have a Jacobian matrix, like in the case of pendulum, is going to be consisting of 2 rows, 3 columns. Now you can select 2 of these rows, columns, to be associated with the dependent ones. If you select these 2, you see what's going to happen is going to be 2 by 2 matrix. And the rest, what is left, is going to be vector with the 2 components. And now, because the one that is related to dependent parts is maybe invertible, probably it's going to be invertible. And now you have a relation between the independent coordinates and all the coordinates. And this is what makes it possible to express the motion in such a way that the constraints are not violated. You got it. You got it. Is this beautiful? The beauty is in your eyes. But don't you see the beauty like the same way that I see this? No? You don't see where the beauty is located? No. Okay. Let me convince that this is beautiful. Because this is beautiful. Okay. But let's first look at this. In this example, which is a crankshaft mechanism, the number of independent generalized coordinates will be what? Is it going to be 1? Like 1 degrees of freedom? Is it going to be 3, like 3 moving bodies? Is it going to be 5, like number of constraint equations? No, that's not going to be even that. It's going to be number of, I don't know what it is, or 9. So which one is correct? You sure about that? 3 bodies. But remember what I said. I said that the number of independent coordinates is equal to the number of degrees of freedom. So what's the number of degrees of freedom? Is it 9? Is this 9 degrees of freedom system? 1 degrees of freedom system. 2 degrees of freedom. So what's okay? Who is so you WhatsApp officer? So what they're saying in WhatsApp? They're confused. They're confused. Like, what is going on? They say 1. 1? Seriously? They say 1 because because of 1 degrees of freedom. You see what I'm doing here? Try to make you confused, because it's important to me to make you confused. And why is that? Because I'm too scared to call the director this time of the day. So that's why. So I need to be careful with that. So I need to be somebody. Shashi, can you be my friend? And okay, so let's take a look. So should we take a look? And then we continue the story. Okay? Okay, let me take this off. This one. Oh, you guys don't see this. Or should I think maybe I should leave this for a little while and get back to this after a certain time, because what makes me feel very, very happy to get 100 and something answers. 100 and something answers. So right now we're below 100. And why this is important? Because there's only one clear indication how you do this in this class. And that clear indication, if you follow the lectures, you're going to do fine. And if not, you will not survive. You will not. Okay, we got 100, but I need more than 100. Okay, 101. Okay, that's okay. I feel semi-happy, not fully happy, because remember what was it before the midterm exam? It was 120, what was it, 28, it's roughly that much. 104 answers. Okay, let me leave this up for a while and revisit that momentarily. Okay? Here, we continue this story. And what follows is that I'm going to speed up a little bit, because I would like you to just understand this concept of coordinate partitioning. The rest is mechanical. It's just mechanical things, and you shouldn't get confused. And the coordinate partitioning is this. What I just said, that you're dividing your coordinates dependent and independent. And like I said, you can do the selection almost as you want. Only thing that matters is that the number of dependent coordinates must be equal to the number of constraints, and the number of independent coordinates need to be equal to the number of degrees of freedom. Almost as you want. There's only one limitation, and the limitation, of course, is this one, because you need to invert the dependent part. So it needs to be a positive definite part, and to guarantee that, you need to use this Gaussian elimination with the full pivoting. But don't worry about that. You don't need to think about anything that complicated. Right now, it's enough to know that you do this division, and that's it. That's all you need to do. All right, now let's continue the story. Now, this virtual displacement of all the coordinates, all the generalized coordinates, can be expressed by independent coordinates, which is the number of degrees of freedom. Can you now see the beauty? It's beautiful. Because when we do this submission here, there is something magical that happens. Something magical that happens is that when you do this submission, then this part of the equation of motion can be set to be equal to 0. Why? Because now the displacement, virtual displacement, is kinematically possible. We are not violating against the constraint. And this works no matter how complicated is your system. Why? Because, look, this relation is coming from Jacobian. Jacobian is coming from constraints. So we are obeying the constraint. So we are not violating against the constraint. Beautiful. So now we can get differential equation that is based on the number of degrees of freedom. How many differential equations? Exactly the number of degrees of freedom. So if, remember, we looked at a little while ago, what was it? I think we looked at the 4-bar, was it the 4-bar mechanism that we looked at? In a 4-bar mechanism, you have 3 moving bodies, and you have a total of 4 revolute joints. You have here, in this system, you have 18, let's put this in a planar case. So you have here 9 generalized coordinates. And then you have here 4 multiplied by 2, so it's going to be 8 revolute joints, constraint equations. So the number of unknowns is going to be 17. So that's a lot. But when we do the substitution technique, the number of equations needed is 1. So the clear difference. Which one is more efficient? You cannot define it. This is hard to tell. There is just a difference in a way that, the teams, this used to be the fact, I don't know if this is any longer valid, but teams that were, multi-body teams located in US, they preferred this team, this way, with a higher number of unknowns, because it's very straightforward, it's very easy to implement and everything. And the European teams were more familiar with, more towards the minimum number of differential equations. Okay, we located in Europe, but my education comes from US. So which one we like more? This one. Higher the better. Okay, it doesn't really matter. You can do that any way you want. That one thing it is important. So whatever you say, the response is. Every now and then I hear this weird statement that this performance is based on Keynes dynamics or this and that dynamics. That doesn't matter. What the equation of motion, what is the way of you expressing the equation of motion? Response is always physics based if it is correctly made. So there is no like different responses depending what kind of the formulation you use. So understand that if you are solving the pendulum using the one method and another method, if it is correctly made, the response should be agreement, with very good agreement. So there should be no difference whatsoever. Okay, so this is it. So this is the story. Now we have these two methods, the one that is based on minimum number of differential equation, embedded equations, where we substitute the constraint inside, or augmented formulation that we even take the reaction forces into account. The problem, of course, here is that reaction forces are not automatically solved, but you can solve them as a post-processing technique if that's what you're interested in. All right, so we were here. So this was a trick that we did. Let's practice this a little bit and let's summarize it. So now concept of virtual work goes like this. You have force multiplied by displacement, virtual displacement. And then you're expressing this one with help of the variables you're dealing with, generalized coordinates. You can express this magic mapping matrix. And then when you're using coordinate partitioning in your constraints, you can express your virtual displacement such the way that is kinematically admissible. Now, when you do all these submissions, you can finally set this part of the statics to be equal to 0. This is a static example because inertial forces are not accounted here. And here's an example to you. So let's look at this example, wrap up the case, and move on to hydraulics. All right. So I have here the mechanisms that we have studied before. So this is the simple 1 degrees of freedom system where there is a primitive joint located here. So this point can slide along the global y-axis, and it can do, this motion is something that is okay. And this motion can slide a global x-axis direction. So those are the two constraints, two primitive joints. One moving body, so it's going to be a total of 3 generalized coordinates. Okay, 3 generalized coordinates are the ones that are denoted here. And now I'm making an obvious choice here. I'm selecting the angle theta to be my independent coordinate. But if not happy with this selection, you can select something else. But this selection is very clever because once you compute your Jacobian, it looks like this. Now what you need to do is that you need to break this Jacobian to 2 corresponding parts. The first part is going to be associated to dependent coordinates. The rest is independent. Okay, now here, this guy, which is identity matrix, is going to be the one that is related to dependent coordinates. This is good choice because later I need to invert it, and it's inverting the identity matrix is super pleasant thing to do. Okay, so it's going to be identity matrix. So that's what it is, so pleasant thing to do. Okay, now the rest is this one. And now you can find this relation between all the coordinates and independent coordinates. Okay, so that's the step number 1. Then where the force is applying. Now I have the gravity force only applying in a system. It's applying here where this center of the body reference coordinate system is located at. So the mapping matrix that maps the force from global to generalized coordinates is going to be very, very simple. Generalized external applied forces consist of 3 components. The only non-zero component is the one that is pointing global minus y direction. Okay? And when I'm using this chain here, this is how I can express my equilibrium. When I do so, this is my force, this is my mapping. When I multiply them together, as it is shown here, I'm going to get the equilibrium. An equilibrium, this is where I can solve the angle. And the angle shows me that if it is like pointing like this, or this is where the static equilibrium can be found. Simple demonstration what the embedded technique can do for you. And now we're going to leave that. Embedded technique, this is where we started. This was the one that was based on coordinate partitioning. And one more problem is, in a dynamic case, we still have one annoying problem. Annoying problem is this guy. Because that includes all the coordinates, and we don't like it because we would like to express the acceleration too based on independent coordinates. So that too is something that we need to use a coordinate partitioning finally, and then we're able to express the equation of motion in a proper way. So this one, when you're expressing this acceleration, and when you're using the coordinate partitioning, in this particular case, the one that is related to dependent acceleration, going to be expressed like this, and then independent is like independent. So now, when I'm using this relation, sorry that I'm going fast, but this is mechanical, so you guys don't need to worry about the mathematical details. So when I use this substitution, the equation of motion is here. That's how it looks. Now what I'm going to do is this. So we're going to take a look at the in-class quiz. So we will have another in-class quiz. And then we're going to look at the one simple example about the embedded technique. But we're going to go that through fast, because this is not the core material anymore. And then comes the hydraulics. How that sounds, like a plan. What did you guys make during the exam week? Because I feel some certain level of unhappiness or something. What went wrong? Was it the exam was too hard, or what? It's just the life is rough. Is that's the explanation? That's good. Because remember, everything that comes without no pain is no value. So this, yeah, exactly. This score is definitely, you feel the pain. You feel the pain, physical pain. So it comes with the game. Okay. Can you feel that your brain is getting bigger all the time? So it hurts. Of course it hurts, because your brain is getting bigger, so it's not easy. So it needs to hurt, physical pain. But it's going to be something that you're going to be happy afterwards. When you look at back, you say, oh, you can make this one of these survival t-shirts. Survive from simulation of mechatronic machine class. Okay, so let me take myself to in-class quiz. And is this one? Oh my God, I'm smiling. I'm smiling. I can tell you why. Not because of the success rate. No, that's not the reason. But the reason for smiling is this. Participants. Number of participants is 127. Fantastic. What is wrong with this guy? Why is keep on bouncing? Okay. Now it doesn't really matter what's even the success rate is 0, I'm going to be happy. Rest of the week, I'm going to be happy. But if it is higher than that, that would be even better. But that doesn't really matter. Results. Success rate is what? 90. 72. No, 72. Ooh, 95. Oh my God, I'm really playing with the fire. This is a high-risk game. But almost done with this high-risk business, because there's going to be one more simple in-class quiz, and the rest is so difficult that you guys have no way to answer correctly. No way. Okay, let me take myself back. Not this one, but okay. So the same example, the one we look at the static equilibrium, I'm going to solve this by using embedded technique, substitution technique. And we have another set of steps to take, and then we're going to get the equation of motion automatically. But first is this. In this example, the number of unknowns. Number of unknowns. Number of unknowns. Most of the class is voting for 5. Think about it. The number of unknowns is going to be based on number of what? Is it going to be number of unknowns? Is it going to be the number of generalized coordinates? Is it going to be the number of constraint equations? Is it going to be the number of generalized coordinates plus constraint equations? Is it going to be the one that is based on number of degrees of freedom? Is it going to be, and the number of degrees of freedom will be like this? Which one it is? It will not help you, definitely not help you. But what do you guys think? Okay, the class is saying here is what? Most of you guys are saying that it's a number of, like you're saying that is this one. But, this is the technique. This is the technique that is based on substitution, embedded technique. So we are embedding the constraints inside. What's going to be the consequence of that? Minimum number of differential equations, minimum number of unknowns. What's the minimum number of unknowns? Minus 10. No. 1? Now, based on your face, you seem to have like full confidence that it's going to be absolutely correct. Okay. Okay, we're going to revisit this right after I'm explaining this example. And here's my proposal to you. Let's look at the example. Then we're going to go back to the in-class quiz. And then what? Break. If you can still find your way out from this lecture room. All right? And then we're going to come back and we're going to get started with the hydraulics. Good deal. All right. So, step number 1, mass matrix. No difference. So we still need to compose the same components that we did when we use a method based on Lagrange multipliers. This difference in terms of assembly process, because the assembly process will be different in this case. All right, so there's nothing new to learn from this first step. So the mass matrix will be the one that is 3 by 3 matrix, diagonal matrix, because the body reference coordinate system is located in the center of the mass. We learned this already when we were younger. A little bit younger than today, all right? Then force of generalized external applied force is no difference in this regard either. So it's all the same business. And we learned this in the case of static example 2. So this is the mapping matrix, which is not even needed because the force is applying in the center of the body reference coordinate system. And then the force vector is the one that consists of 2 components, 0 minus mass multiplied by gravity constant. And then quadratic velocity vector, that's going to be equal to 0 because we learned it already a while ago that that's the case if the body reference coordinate system is located in the center of the mass. B, here comes the first complicated component because now we need to use this coordinate partitioning. And I'm selecting the identity part of my Jacobian to be dependent part, rest is going to be independent. And when I'm expressing this B, is need to be this identity part to be inverted, and this is going to be my B matrix. My D matrix, which is the next step, I need to use the coordinate partitioning both acceleration level. And yes, this is a big pain. This is going to be not pleasant to do, but thanks God we have a symbolic math tools, so they will do the trick for us. So once you do this, then finally, this is the D matrix. I'm not even looking at the details. The D matrix look like this. a final assembly process here. I have not made the mathematics, but look at the number of unknowns is equal to the number of degrees of freedom, which is 3. Okay, let me take myself back. I need to rush myself because otherwise I cannot say the correct answer. Uh, oh, you cannot. Oh, yeah, yeah, of course not. Okay. But again, I cannot say what is the correct number, what is the correct number of unknowns. But this example, then in this example, the number of unknowns will be. I'm not going to say that because, as you know, here in the class we have how many students we have in a class roughly 20, 40, something like. Majority of the students are participating online, and I don't want to help them too much. By the way, guys, why are you coming here? Why don't you follow the lecture online? Online is artificial. Yeah, I know. The big problem in online is that you get distracted so easily. So let me check my email. Let me check my YouTube. Let me check my Discovery channel. Let me check my this and that. And all of a sudden you recognize, oh, it's all gone. So the lecture is gone. And I did not even notice that it started. So this happens so easily. Here you now have no other choice than listen to me. And I make all the fun out of that. Okay, we got this many students. Now, guys, what's going to happen is that we're going to revisit this answer right after the break. Break is going to be how much time you need to recover. 5 minutes. 5 minutes because it's been light. And so on. From this, what follows, like finally, like I promised, and now it's going to be the true case. We are not going to discuss about multi-body anymore. Please come back. So it's all about the hydraulics. Let me tell you something that is good to you to be aware of. Because the modeling of hydraulics is not same kind of the science than modeling of mechanical components. Mechanical components, look at what we did. So everything is very much physics-based. Whereas in hydraulics, we're going to get a lot of parameters. We are not quite sure what they're supposed to be. And this is going to be not so exact science than modeling of mechanical components. Still, surprisingly enough, when you build a model of pretty much any hydraulic circuit, the representation of reality is very accurate, even though that sometimes we need to guess some of the parameters. Or let's say that we don't know them in details, but still they seem to be representing reality fairly well. Okay, you guys go and relax, come back in 10 minutes. Okay, Team Finland is back. Go Finland. Do you know how I know that this Team Finland? Because Team Finland is always sitting in a pack. Always, always. So it's easy to recognize. Okay. All right, guys. So let's go. Okay. Yeah. All right. So we are here. So we look at that number of unknowns in this example is going to be what? Okay. We got 129 answers last in-class quiz. Was it exactly the same number? I think it was. Okay. So let's look how we're doing. Success rate 52, 50, 50, 51, 51, 90, 90, 90. But what about 100? Not 100. Okay. Ooh, so same. Okay. Now, guys, here's my advice because we need to say goodbye for this easy in-class quizzes. So you guys need to join into this WhatsApp group. How you can join that? You can join by look at the first lecture of this course. Look at the first slide, if I remember correctly. Copy this QR code, and you can log in. This WhatsApp officer will allow you to get in because you guys need to collaborate more. This is good. This is still pretty good, but it could be. It's not 100%. Close, but not exactly 100%. Okay, so let me take myself to hydraulics. I need to take this. Oh, no, not this. Because there's a certain sequence that I need to follow, otherwise it's not displaying well. Okay, now it's displaying well. Okay, embedded technique versus arithmetic formulation. Embedded technique, number of equations are based on coordinate partitioning. That's the trick we did. And equations of motion do not include the reaction forces. Yes, and very few number of equations are needed. Large number of equations of motion are relatively simple to deal with. Reaction forces, look at that, are included in the equation of motion. Okay, mechanical modeling. We need to revisit this as soon as I'm going to give you this simulation assignment. But you see something important here. This is all about thinking, and not about doing. You know, there's one famous student that got the degree a while ago. When he was modeling, the clicking frequency of his mouse was more than 100 hertz. So he was really clicking like hell. But success rate was very, very low. So that's a good example about not too much doing, too little thinking. So make sure you're doing opposite. Think more than do. But we need to revisit this list a little later. And now follows hydraulics or actuators. I want to first mention this actuator business. Like I mentioned, so we're going to focus on hydraulics here, but you need to be aware of this. The hydraulics is a little bit less in fashion than it used to be a while ago. A little less in fashion because hydraulics is suffering from very traditional problem, which is complicated to solve. Leakage. Whatever you see a hydraulics, you can see leakage too. And this is something that is a certain industrial application, heavy mobile machinery too. The leakage is an annoying problem. And you see this clearly in, let's say, like paper making machines. Whatever you have a hydraulics, you have a bucket of oil because of the leakage. And the leakage make things to look nasty. They are not pleasant looking. Everything looks messy and so on and so forth. So the leakage is amazingly complicated to solve in a proper way. Now, of course, another thing that is a little bit of problem in hydraulics is that, you know, it's not considered to be like, is it like black screen? Okay. So how was it so that the last time too, when we started to lecture, there was something? display. Okay, I think that it is. All right, I think it is okay. Now I make the incorrect sequence again. Okay, how is looking? Is it getting back?
We can see it.
So you can see it now.
Yeah.
Okay, so in heavy machinery, the typical way to use a hydraulics is that there is a diesel engine that is connected to pump. The pump is then is producing the energy, the hydraulic cylinders, and this is the way you do the actions in heavy mobile machinery. Now there is a heavy trend, which is electrifying. Try to use electric drives more than at the moment. And electric drives is a kind of the good idea. The problem is that the power density, I mean, physical size of the actuator versus the force it can produce is not as good that in a hydraulics. Hydraulics actually the power density is the superior, is really good. The small dimensions you can produce a lot of forces, which makes that to be very, very good in heavy machinery. Now they've been every now and then like different ideas like how to make an actuators at another level or how to create another type of the actuators. The good example that was that was a little bit in fashion a little while ago was a water hydraulics. So instead of using oil, let's use the water because then it doesn't really matter if there's a leakage because if the water comes out, fine, you can drink it if nothing else. So it's not going to be anything too dangerous, environmentally very friendly, green even. Problem, of course, is this, two big problems. First of all, even though that there's this statement that the water is the best lubricant ever, it's not great lubricant. So it's not very, very poor lubricant. Because of the poor capability to be a lubricant, you need to use a very exotic materials like ceramics. Okay, then the price goes up. Another big problem is this, that if you take a glass of water, you leave the water to your glass for a month, and you come back, you take a look at the water, it's no longer water, but it's green. And it's not just green, but there are monsters that coming, I'm going to come and kill you out from the water. These major size monsters, they are dangerous, they can eat you, like no problem. So what you need to do to get rid of these monsters, you need to put a little bit of poison to water. Okay, that's about the environmental aspects about that. If you're using some poison together with your water, so it's not going to be very good anymore. So that's something that water hydraulics is less popular at the moment. But if you look at the developments made for hydraulics, conventional hydraulics, the operation principle is still pretty much what it was 100 years back. So there have been some minor improvements like load sensing pumps, a little bit better valves and so on and so forth, but principle behind is not much of a difference. The recent developments that are related to digital hydraulics comes with a big promise because the problem in hydraulics is that these keep on losing quite a bit of energy. That losing energy is not very much in fashion today because you're supposed to be very, very worried about how much energy you're actually using. It's hard to harvesting energy using hydraulics. And basically, the controlling of hydraulics is based on pressure losses, which is equal then energy losses. And this is something that is a big problem today. We'll see what comes out of from this digital hydraulics. And we're going to learn the basics of the digital hydraulics a little later in this class. But let me ask you guys this. Have you heard about the digital hydraulics before? No. Okay, I'm going to explain it to you. But again, there's a big promise that it's going to be something that is going to make things to be less consuming energy. But still some basic problems to solve. All right, so actuators. This guy is stuck. So what is up with this? This is like completely dead. Am I still streaming? But even the mouse is no longer working. I need to take myself back here where I was. Oh yeah. No, I don't get this thing. Like, why is not? How come this is not willing to collaborate with me today? Nothing. Keep on taking me this weird place. Okay, now it works. So my keyboard is working. I was here. Okay. It's almost like there is, if I put this in a presentation mode, then you can see it. Yep, now it works. It works. Okay. A little bit of examples where the hydraulics is being used. Okay, the animations is not displaying well, but of course, different kind of crane structures. This is typical example when you can make use of the high power density of hydraulics. Here that you see that the size of the actuators is not huge, so they are pretty lightweight, which make them to be optimal to be used in different kind of crane structures. This is a pilot drive. Again, the animations is not working well, so it finally is coming. But just a different kind of controlling of this big boom is made by hydraulics. This is a deflection compensated roll, which is used in a paper making process. This is a top of the roll that I'm specialized to. Seriously, it is. It is because no, I cannot display this to you. Okay, it works in a way that oh, now it displays. There is like a shaft, this shaft that is standing still, and then there's a shell that is rotating, and between the shaft and the shell there's a tonal bearings, and tonal bearings that are very specialized because they can introduce the forces to compensate the deflection. As the name deflection compensated roll, that's where that is coming from. Typically used in different kind of paper making processes, in like post processing part, and even in the using a part of the machine itself. All right, and how did I specialize that? Because I was a product development engineer a little while ago, more than 25 years ago, in a company called Valmet, making these paper making machines. Okay, here is an example about hydraulic modeling, which I'm not going to use, because this kind of hydraulic modeling is based on this kind of icons. You just put these icons in your screen, and then you go. We are not going to use this, but instead, we're going to enjoy the life more. And the way we're going to enjoy the life more is that we're going to create the equations that are behind of these icons. This is going to be the way we're going to model the hydraulics. And yes, you're right. It's going to be a big pain because one single mistake in one of your equations is nowhere near to work properly. But educationally, best, because can you feel this? Can you feel this noise? It's coming when your brains are bigger, getting bigger all the time. They definitely will do so when you're going to use this kind of manual modeling procedure. But manual modeling procedure is not used in real life. In real life, when you're making models, you're using one of these tools, and there are plenty of different kind of tools. You just place in the icons, you're selecting proper parameters, you're collecting the components together, you're good. You're good to go. This is a typical modeling procedure. And this kind of modeling procedure is available in Media software if you decided to use Media software, and is going to be available in many other multi-body based software, because obviously if you're guessing the forces, you're guessing too much. So it's not going to be physics based any longer. All right, let's start modeling of hydraulics. So first let's take a look at the fluid itself. In a fluid, we have two very important properties. And one only out of the two is important, another one less important. Okay, so the properties we need to take care of when we are modeling the hydraulics fluid. We're getting started from the fluid itself, is viscosity and the bulk modulus. The one that is actually important for us is a bulk modulus, because the bulk modulus is defining the flexibility of hydraulics. Often, flexibility of hydraulics is equally important, even sometimes more important than the flexibility of mechanical component. And that's simply because the fluid is compressible. And because the fluid is compressible, then of course, cylinders too, if you put them a lot of force, they will act like a spring. And because they will act like a spring, this flexibility is something that is visible often, particularly if there's a like mobile machinery. You can see that, okay, the hydraulic cylinder, it is actually getting shorter and longer because of the loading itself. This particular feature is described by bulk models. The one that is less important is the viscosity. Viscosity is less important because viscosity only comes into play when we're dealing with the laminar flow. And for your information, we have two different kind of the flows that typically takes place. We have laminar flow and turbulent flow. And turbulent flow is a dominating, particularly in a heavy machinery. It's like 99.90 something percentage of the case is turbulent flow. Laminar flow, yes, every now and then it takes a place, but it's not dominating. And it's not dominating because the turbulent flow takes a place when the pressure difference is big. Okay, unclear statement. But big here is like if the pressure difference is more than 3 bars, which is not much. Usually the pressure difference through the orifice, through the components, is like tens of bars, easily, if not hundreds of bars. Let's say tens of bars. And that makes it this turbulent flow to be way more dominating than laminar flow. There's an exception, of course. Exception is that like we look at this deflection compensated roll. In deflection compensated rolls, these loading shoes, the ones that are located here, the fluid goes through these shoes. And this type of this, because this is a very long drilling, this flow type is a laminar flow. But it's not very common. And this is something that you see in engines, perhaps in certain locations, but heavy machinery like actuators, you don't see that very often. Okay, but two properties, and today we're going to look at both of them. We're going to take a look at we're going to get started from the bulk modulus. Remember, it's like elastic modulus using the strength of materials. So something that defines how flexible is your hydraulics. Okay, and the viscosity is another thing. But let's get started from the bulk modulus. Definition of bulk modulus is pretty simple. It's something that we can find it out when we are having a container that is stiff, let's say undeformable container, which is not, you cannot find this in a real life because everything is deformable in real life. But let's just make a like imaginary container that is made out of the hyper composite something which is not capable to deform. Okay, and this is a container here, the one that is a green in a color, and then you have a lid in your container. The lid too is something that is unable to deform, and what you're going to do is that you're going to compress the lid inside of the fluid. And what will happen as a consequence of that is that the pressure within the fluid will increase because you're compressing it. So the same thing like air. So this is not that much of a difference than air. The compressibility of air, like I mentioned, is more than 1,000 times lower than a fluid. But when you're compressing the lid, it comes down and the pressure increases. Now the relation about how much the lid goes down, how much the volume is getting smaller versus the pressure increase. This is going to be the definition of your bulk modulus. And I think that I said that in correct order. So it's all about how much pressure is increasing divided by how much the volume is decreasing. So that's relation, or this is a definition of bulk modulus. Very, very simple, not too complicated to memorize. So bulk modulus. Okay. Now, every now and then you can hear, okay, right, but the fluid is incompressible, so it's not, this is nonsense, this is not you can find in a real life. Yes, you can find this in a real life, and I have a proof about that. First of all, the compressibility of air is that, everything that we do here is based on the compressibility of air. Because what happened here is I'm talking, and there are waves that are leaving from my mouth. It goes to your ears, and you hear me. I'm not sure if you can understand me, but this is all because of the flexibility of air. Okay, what's going to happen if we're going to fill this legs room by water. So then it's going to be like when you go to the swimming hall. Swimming hall, you can go underwater. I can speak to you, and then you can hear me the way you probably hear me today, like this. But you hear me. You still hear me, not understanding me, but hearing me. Okay, here's a proof that the water is flexible too, because these waves are traveling within the water too. All right. Now, let's forget about this understandable business. So let me look at this in general case. So now the unit, or let's say that the container we look at was a special container because it was unit in a size. And it's hard to find always a unit in a size container, so we need to generalize this definition. We can generalize that by dividing the change of the volume by the volume size itself. So when you do this math, your bulk modulus definition is going to be minus volume size multiplied by pressure difference, how much pressure is increasing, divided by how much volume is decreasing. So that's going to be definition of bulk modulus. Here comes the first big assumption. You know that there's a bulk modulus in real life. Depends on many different things. But in the modeling, we don't care. Usually we make an assumption that the bulk modulus is constant. Just to give you an example, how is not constant is that this picture that is a little bit blurred, but I have here temperature, which ranges from, this is 10 degrees to 120 degrees. And then I have here the bulk modulus, like how many megapascals. And then I have here different curves that are representing the pressure within the fluid. You see that it is actually a function of the pressure. It is function of the temperature. And this makes things complicated. Usually, we don't care. The usual way to model the flexibility of fluid is just to set that to be constant value. And the good approximation would be somewhere here, like roughly here, this region. Because the typical pressures we're dealing with are less than 350 bars. And the typical temperature is in typical this region. So the okay assumption would be 1,500 megapascal. This is a typical assumption. You can play a little bit with this, but you'll be surprised that even if you play a little bit with this parameter, the effect of responses is not necessarily super great. There are components that are going to make a more significant effect than the compressibility of the fluid itself. Okay, what is this effect that makes this to be more flexible? What makes for hydraulics actually to be more flexible than the fluid compressibility itself? That, of course, is real component. Like I mentioned, I explained this concept to you by saying that the container is actually rigid. But this kind of the container is not in real life. In real life, there are hoses, which is typically rubber made, and the rubber is very flexible, even though that there is a steel net inside of it. There are typically certain amount of dissolved air within your hydraulics. Dissolved air. Oh my God, that's horrible because remember, air is having the bulk modulus, which is 1 instead of 1,500 megapascal. So if there's even a little bit of dissolved air, it increases the flexibility a lot. These different components, they increase in the flexibility a lot. And these are the ones that are playing the major roles in terms of flexibility. Okay, we need to figure them out because they are actually applying and they are making a difference in responses. How is that we can make that to happen? Well, we can make that to happen by combining something that is called effective bulk models. It's like real bulk models, to be more clear. So the one we learned in the previous slide was a theoretical bulk models. Hard to find in a real life because in real life there's these components, these factors that I just explained to you, reducing the bulk models, making things to be more flexible. Because you understand the higher the value, the more rigid is a fluid. Lower the value, more flexible is your actuators. Clear? Okay, right. Just checking this is making good. All right, then how is that we can compare this effective bulk modulus? All right, let's complicate things. Let's look at the setup where instead of there's one container, there's two containers. Now in two containers, where we are assuming that the pressure is equally distributed. This is something, by the way, that is going to be very, very important when we are computing the pressure. We need to discretize our hydraulic circuit to volume where the pressure is assumed to be equally distributed. Okay, so here, I think it is a fair assumption to say the pressure here is going to be the same than here because there's nothing that introduces pressure losses. There is no like trillings or throttles or anything like that. There's a clear flow traveling back and forth between these two containers. Okay, so here is my first container, and the size of the first container is a V1, and the second container is a V2. And the bulk modulus is assumed to be the same, the fluid bulk modulus, because the same fluid travels back and forth. So here, this is a B1, B0, B0. Let's do the following. Let's look at how much is the volume as a total. So total is a container 1 plus container 2, which is the same that the volume size 2, simple like that. So let's change that. Let's change the volume of the fluid. That means that also the containers are getting a little bit bigger because, they are expanding a little bit. And when we're using this definition of bulk modulus that is written down here, now substituting that information here, so on and so forth, this is how it's going to be written. And now if we're going to solve this, that is called effective bulk modulus, it's going to be solved in a way that it's going to be based on how much is the flexibility of the fluid itself, and how much is then this is a fluid in a first and second container flexibility of the first and second containers, and then once we make an assumption that roughly this container size is the same than the volume size, we can simplify this as it is shown here. Okay, let's stop here. So this is what you need to compute. This is called effective bulk modulus. This is what we are after. And it's based on, in this particular case, it's based on 3 components. First component is a flexibility of fluid itself. This is one that we can set to be 1,500 megapascal. And then we have a flexibility of the first container. How much is that? This is what we need to compute separately. That is with respect to the size of the volume itself, container itself. Okay? Flexibility of the second container and the corresponding volume size. Now, if you're dealing with a steel hydraulic cylinders, their flexibility is actually not very big. But as I mentioned, the hoses, they are actually introducing quite a bit of extra flexibility to the system. And of course, one component that is missing here, which is not yet even accounted, is what about the dissolved air? That should be added to this equation. Dissolved air, same way. So you need to make an assumption about what's the volume that is occupied by air, and the flexibility of air is going to be extremely low. Okay, we are not going to model in this way, but let's look at a little bit about what we learned from the experiments. So here is an experiment that I need to sit down to explain it to you. Okay, I have here a curve which is in a function of x and y axis. The x-axis here is a pressure in megapascals. And then the bulk modulus here is in the y-axis. And then I have different kind of scenarios based on the amount of dissolved air. And the scenarios are such that there's no dissolved air. So then the bulk modulus is constant all the time. And then I have here percentage, which is 2%. 2% is already something that, when the pressure is not very big, is dramatically reducing the bulk modulus. And then there is a percentage which is, if I see this correctly, this is 5, 10, 15. 15 is not realistic. 10 is not realistic. But easily, they could be 2%. How much exactly? This is impossible to know because air can be dissolved the system in two different ways. So this is extremely difficult to know. Typically, what you just need to do is make an assumption. How is that the air can end up to be in your system? Well, of course, when you do the assembly, there could be air in your actuators. Of course, should get rid of the air by running the cylinder from full length to be as short as it can be. But always there is a possibility that there's a certain amount of dissolved air in your system. So actually, getting rid of the dissolved air like completely, almost mission impossible. Very difficult to do so. Okay, so this shows what about the containers, how much they are introducing the flexibility. Here's my last slide, because I see you guys are tired. Why is it? Is it because of the rough week? Is Monday? How can be rough week so far? Because you enjoyed to be not having any lectures and now you are having a hard time to come back, or what's up? What's the deal? No need to answer. Okay, here's the last slide for today. So you have a hope. So you will survive. So be with me. It's going to be fine. Okay, last slide. This is an experiment where there is what about if there is a hose? And how is the bulk modulus, effective bulk modulus, to be more specific in case of hose? You see that, okay, first of all, this is heavily function of pressure inside. And you see the numbers I have here. Of course, this is at 10 power 1. So this is actually 400 megapascal, this particular value here. So you see that if you compare the flexibility of fluid, again, it was 1,500 megapascal, is reducing a lot. Now, what do we learn from this? If you have a problem in the flexibility of hydraulic cylinder, go and reduce the length of the hoses. This is the first thing you can do. Make the hoses to be shorter than originally. Replace the hoses by pipes, because the pipes are much stiffer than the hoses. But if there's no other way, then you just need to deal with this lower flexibility. And again, lower flexibility is not necessary. Typically, it's not because of the flexibility of fluid. Yes, that plays a certain amount of role, but the more important role comes from the hoses and other components. So try to reduce that as much as you can, and then you have more rigid hydraulics. What's the benefit of more rigid hydraulics? Well, depends what you want it to do. Well, at least you can get rid of this annoying flexibility that sometimes you need to wait until it's damped down, so you don't need to worry about that. And it feels better because it's like more solid. Okay, so this is the opening session about the hydraulics. We continue with the hydraulics. So what will follow is we're gonna discuss about viscosity, which is not very important for us, next week. And then we're gonna do, let me take myself back here. Then we're gonna discuss about something that is very, very, very important. That is called land fluid theory. So all the modeling of hydraulics is gonna be based on land fluid theory. It's a concept that is not overly complicated, but you do need to follow my explanation. Do you still have, guess what? Can-do attitude. You still have a can-do attitude. Come back next week with your can-do attitude. Okay, have fun. Take it easy, guys. See you next week. I'm supposed to be back in my office in 5 minutes from now, so it's going to be a little bit rough. Okay, let me stop the streaming.